Hey everyone, welcome to my channel. This is a voltage regulator out of my Ford 5000, or more correctly, my Ford 5200 tractor. My tractor was made in England, and that's why I wasn't surprised at all to find that the voltage regulator, which I have right here, was also made in England. It says so right here. In fact, it was made by Lucas Electrics, a very prominent manufacturer of electrical components for automotive and other industries in England. A lot of Jaguars had Lucas Electrics. In fact, the Lucas Electrics and Jaguars were known to be quite problematic for many people. I think the running joke was that Lucas was referred to as the Prince of Darkness, kind of a pun on, being in the dark because of not being able to have good electricity flow to your lights. Boy, that was talk about ruining a joke, right? Anyways, I'm not really here to comment on how good these components were. I'm here to diagnose and try and determine what's going on with this regulator. So, just a quick background on the tractor. When I first started working on the tractor, I have a dash warning light that when you turn the key on, it is lit. And once the tractor starts and the generator starts outputting voltage, that light is supposed to go out. My light is staying on. The first thing I did was check for voltage output from my generator. I had no voltage output from my generator. I then fully fielded my generator, which if you're not familiar with that term, just Google that, fully fielding a generator. It's I'm not going to get bogged down in other stuff here. Just basically all you need to know is that my generator wasn't working. I disassembled the generator, I cleaned the commutator and the brushes, lubricated what needed to be lubricated and put it back together, and then found that I still had no output. But when I would fully field the generator now with the tractor running, I get plenty of output from the generator. So I now know my generator is now working, but the problem is it's not getting the field coil voltage it should be getting from the voltage regulator. So it's a pretty basic system. You've got the generator, you've got the voltage regulator, and you've got the wiring harness in between, and you've got the battery. That's basically all there is to it. Everything else is all what we call the load, the stuff that comes later. So this is a Lucas model RB340 regulator. Oftentimes you'll hear regulators referred to as 3-terminal and 4-terminal regulators. You might notice that there are 1, 2, 3, 4, 5, 6 terminals on this particular regulator. If you're looking for terminals and you don't see them here, sometimes they hide a terminal underneath here. This is not really a 6-terminal regulator. There is no such thing as far as I know. The first thing to notice is that these 2 terminals right here are actually tied together. It might be a little hard to see, but this metal right here is common. This metal is all common to each other. You can see it right here. This terminal is marked with a B on the top. That is the terminal that goes to the battery. On some voltage regulators, they will have different letters to signify what terminal does what. Sometimes the terminal will be marked BAT or even BATT. The next terminal over right here is marked with an F on the top. This is the field terminal. This goes over to the generator. The generator will have 2 connections on it. One of the 2 connections will be marked either F or FLD, or maybe sometimes FL, but I guess even my notes here say that even FIE, which is interesting. First few letters are field, but that goes to the field terminal. Again, don't want to get too bogged down with details, but basically the field terminal is the coil that is in the outside of the generator housing that actually controls the amount of output from the generator, as opposed to the other coils, which are the spinning ones, which are the armature. The next terminal down is this one kind of down here off to this underneath, offset. This terminal may or may not exist on your regulator. This terminal is marked WL. This is the terminal for the warning light. This goes to the light on my dashboard. The next terminal, this large one right here, on this particular regulator is marked with an A. This is for the armature. This is the connection that goes to the generator. Notice that the bat terminals and the armature terminals are the largest because they carry the most current. The majority of the power flowing in this system is going in and out, depending on which direction, through these terminals. This last terminal over here to the left is marked with a G. This is the ground terminal. On some units, this will be marked with an E for earth. Oh, I almost forgot. On some regulators, this A terminal, the armature terminal, may or may not be marked with a D. I don't know what D means. Last but not least, on some regulators, there will be an additional terminal marked L. L stands for load or lights, more likely load. On some tractors, there will be a separate wire that sends power from the regulator out to the light circuits and the other accessories in the tractor. So you don't need to use this if the tractor wasn't previously wired that way for it. Now that we know what all the terminals are for or which direction they go, let's take a look inside. The first thing you want to do is visual inspection, is you want to see whether or not the thing got wet. So if you look on the back side here, you can see there's a lot of greenish blue corrosion because when copper corrodes, that's the color it gets, right? So we've got some potential issues here with connections right off the bat, because these connections right here are actually what make the electrical connection between these terminals and the internal coils we're about to look at possible. So this right here could spell trouble. These devices right here, by the way, are resistors. They have thin filaments of wire wrapped around a typically like a ceramic type of substrate, and they actually have a little bit of electrical resistance, and they're part of the circuit. This is a larger one that is tapped in the middle. So 2 screws here and the cover comes off. We look inside, actually looks pretty good. There's only the slightest indication of corrosion in here. They actually don't look bad at all. So I would say that that gasket was probably still doing a pretty good job. In fact, I've had this off, just loose like this, under the hood of the tractor, and this could even just be from just me opening it up and having it in the humidity. So what we've got is we've got 3 coils or solenoids, or relays really. This one over to the far right is known as the cutout relay. The cutout relay is responsible for disconnecting the connection between the battery and the generator depending on what's going on in the system. So I'll give you an example. If the tractor's running and the generator's making power and we want it charging the battery, then we want this closed. However, if we shut the tractor off, if this relay didn't exist to cut out the connection between the two, what could happen is the generator would be sitting there not spinning, and the fan belt is keeping it from being able to rotate, but power from the battery now is going back towards the generator, trying to turn the generator. It's trying to turn the generator into a DC motor. And the problem with that is twofold. Well, for one thing, we're losing power, we're wasting power from the battery as it drains. So we're going to drain the battery. But to make matters worse, we can actually end up damaging the generator because the generator is not designed to have voltage input into it while it's unable to rotate. It gets angry and bad things happen. So we don't want that to happen. So by design, this relay right here is designed to open and close as needed depending on the situation that's going on around it, as far as, is the generator making power or is it sitting there doing nothing? These two relays are to regulate the voltage and the current. And the way these relays work is they are basically sensing the current draw through the system and the voltage level, because you're going to constantly have all different kinds of things happening. On the one hand, we've got the generator over here. The generator, depending on the RPMs from the engine, the voltage coming out of the generator is going to go up and down, up and down. Well, that's why we need a voltage regulator in the first place. Because if you had your lights on and you didn't have a voltage regulator, well, as the RPM speed up, the lights would get brighter, and as the engine slows down, the lights would get dimmer. We can't have that, so we've got to have a way to regulate that voltage and keep it constant. The other thing that's going on is we've got the battery over here, that once the battery has done its job of starting the engine, the battery is sitting there and it's thinking, hey, you know, I could really use a little bit of voltage to recharge me. But I'm a stubborn battery, and if I've got about 12 volts in me right now, I'm not going to let you charge me up to anything higher than that unless you put more voltage in me. So this generator has to be able to overcome the voltage in the battery. That being said, if the battery is fat and happy and fully charged, we don't want a lot of voltage being forced into the battery from the generator, because then we have an overcharged situation and the battery gets unhappy. So again, I don't want to get bogged down too much here, so I don't want to get into the mumbo jumbo of exactly how these shunt windings and series windings and coils on these things work. All you need to know is this, that this is basically an electromagnet that is, when it's energized, is able to pull down on this part on the top here. And this particular design, it uses a leaf spring right here. So when the magnetism power of this coil, when this coil is energized with enough power to overcome this spring, it's able to pull this down like I'm doing with my finger. And what's happening is, you'll notice there's a contact right here. Right there is almost like a set of points. The other one is just like that one, only it's buried in here. And then the cutout relay, if we flip over to this side, the cutout relay is actually buried down inside. Well, it's actually even easier to see it from this side. It's right here. You can always tell the cutout relay, because if you look down inside here, it's kind of hard to see it because it's kind of getting in the way, but that contact is open. So the cutout relay is normally open and has to be pulled closed, whereas the current and voltage regulator relays are normally closed and get pulled open. So while this is in the tractor or vehicle running, there's kind of a dance going on in here where these contacts are rapidly closing and opening as needed, depending on what the situation is. These two are going to be chattering like crazy when they're doing their job, and this one right here is maybe a little bit more calm, but you get the gist of it. So, you're talking about failure points with this system. Well, you could have an open coil on any of these solenoids or relays. You could have bad contacts. There's also, burnt or dirty or corroded contacts. There are adjustments on here that you do not want to mess with unless you really know what you're doing. These adjustments right here are actually you can see it's almost like a cam that's going to be pushing up on this metal leaf spring. So what we're doing there is the further we push that up or let that come down, the more or less voltage in this coil is going to be required to pull it closed. Furthermore, we have an adjustment right here. There's a lock nut, it's a jam nut, and a screw that actually will move one side of this contact in and out. So that obviously will have an effect. So these adjustments, that one right there, and its twin down inside here, these two right here are going to be for setting the point of opening and closing for these two relays based on current flow and voltage. So since this thing's really just made up of interconnected relays and a couple of resistors on the backside, it's actually a pretty simple circuit to examine as far as for faults. The relays couldn't be more simple. Basically, you've got a core that has a winding wrapped around it. In this case, it's got a very fine winding wrapped around the central core on the cutout relay, and then it's got this much heavier winding around the outside. But the heavier winding around the outside, you can see how robust it is. That's not going to be your problem unless something went so wrong that the connection got so hot that it melted the solder connection here and like caused it to come undone. But this actually, this is one end of the coil right here. It wraps around this, leaves this coil, goes to the next coil, wraps around that, leaves the bottom of that coil, comes around, makes one wrap around the very outside of this coil, barely getting involved with that coil, and then coming to over here. So from here to here, if we put our ohm meter across from here to here, we're only seeing the resistance of this very thick copper coil that doesn't have that many turns in it, so it's very low resistance and easy to see that there's nothing wrong with that. Where you can have a problem is the finer wired coils, which actually exist on only two of the three coils. I mean, two of the three relays. So the cut in, cut out relay has a fine wire coil underneath it, and the voltage sense relay has a fine wire coil underneath it. The current one only has this one big brute force heavy wire. So this coil, if it fries or gets burnt, oftentimes it will be discolored. There's some paper or masking tape around it that kind of shields it so you can't really see the whole thing, but oftentimes you can actually see that instead of being that nice color that you see down in there, that nice pinkish red color, that'll often turn dark because the enamel on the wire will burn before the coil burns open. It'll overheat. This one is even harder to see because it's got this larger coil on the outside of it. But we can test those coils, sort of. The problem with these coils are that they're actually in parallel with each other. So the two connections from each end of one of the coils are actually connected across the two connections for the other coil. The resistance is very low, but it is measurable. But the problem is because they're in parallel across each other, this one coil could be open, and as long as the other one isn't, then you're going to still get a reading. If you get an infinite resistance reading when you're across the two coils, then it would mean both coils have burned open. So if I wanted to check and see if both of them were burned open, this little thin wire right here, is actually one end of one of these two windings, and then there's another one kind of right behind it. That actually goes around through this insulated wire right here. It's covered up and snakes over to this other one over here. This is the other end of that coil, And then this little tiny thin wire is the other end of this coil. So if I hook up to here, this lug, and to here, this connection, I am now across both coils. And I'm getting about 6 ohms. Now, I know from experience that if these are two resistances in parallel and they happen to be identical, then what we've actually got is like two 12-ohm coils in parallel would give us about 6 ohms equivalent resistance because of the way that the calculations work. Again, Kirchhoff's voltage and current laws basically tell us what's going to end up happening here with Ohm's law and all that. But we're trying to simplify this, right? So all you need to know is if I get infinite resistance here, if I get this kind of a reading over limit, like it's wide open, the only way that can happen is if both of these coils are burnt open. The fact that I'm getting this reading tells me that either one or both of those coils are good, but doesn't necessarily guarantee that they're both good. But let's make an assumption they are and move on to the next thing we can test. All right, so let's say for the sake of argument that we feel pretty confident that the coils, the electromagnets that actually pull these down when they're supposed to, are actually working. So what can we check next? Well, the next logical thing to check would be the actual contacts themselves, the points, so to speak. These little connections right here. Now, what do we know about them? Well, we know that, as we had already discussed, that this one over here is normally open. So right now, there should be infinite resistance between this side of the connection and this side of the connection. And we know that these two right here are normally closed. So right now, this contact should be closed. So there should be very low resistance between this arm, which is common to this frame, and the seat of that contact on the back side here, which through a brass bracket and an insulator and rivets is actually electrically attached to here, and then this copper strap over to the other contact. Again, through these rivets, through insulators, to this brass bracket, to here, and then through the closed contact up through here to the frame on this one. So we just determined that these two contacts are in series with each other. So in order to test these contacts, it's pretty simple. All we need to know is which of these connections out here are associated with which of the frames on these relays. Well, the frames on these two relays, the cutout relay and this relay, are both directly connected to the armature terminal right here. So if I go between the armature terminal and the frame on this relay, which is also this lug here, all right, I get 0.2 ohms, which is the resistance of my leads, basically. So it's a direct connection between here and here. So if these contacts are indeed closed like they should be right now, then I should see that same low resistance if I go directly to this side of the contact. And I do. All right, so far so good. But see, I'm on the side of the contact that is actually directly connected to the frame. So I haven't tested that contact yet. Remember, this contact on the back side actually goes through the frame, is insulated from the frame by this insulation material, and connects to this copper strap right here. Watch what happens when I put the connection on the strap so that now I'm looking directly across that contact. Whoa. We've got like, that K means 1,000 ohms. So it started at around 200 and something thousand ohms, and it's rising. Why is it rising? The reason why it's rising is because those two contacts aren't making a connection to give me very low resistance, but they're just close enough so that they are acting like a capacitor. And right now, that capacitor is charging. The battery in my meter is literally charging the plates in that capacitor. And that's why that's rising. So we've got a problem right there. So now I'm just going to push down on this, which would simulate the coil being energized and pulling those contacts open. And what we should see is we should see infinite resistance. No, we're seeing something else. So that might be actually the resistance of something else in the circuit, like one of those resistors on the bottom. So I'm not too concerned about that. I'm more concerned about the fact that this just isn't closing. If I push hard, I can actually get it to go down lower, but it's still not working the way we want it to. So that's problem number one right there. This contact is currently supposed to be closed, and it's acting like it's got over 500,000 ohms on it. All right, so now let's look at this contact right here and see how it's acting. The frame on this particular relay is actually common to this terminal right here, which is the field terminal. So if I go from this terminal right to here on the frame, you'll see there's very low resistance because I'm basically looking at just this big hunk of metal here. But then it goes down this arm right here to one end of the contact. And then it should be going across that closed contact right now through these rivets right here, being insulated from the frame by this insulating material, back over to this copper strap. And again, we've got the similar problem. We're looking at very high resistance, over 500,000 ohms and climbing. So this contact also, even though it's currently in the closed state, is not acting like it's closed at all. Well, as long as we're in here, we might as well check this last contact. This is the contact that's normally open when nothing's energized, so we're going to have to manually close that contact. Where does that contact connect to? Well, the frame on this relay actually is also directly connected to the armature terminal. And then the other end of the contact is right here, actually goes directly over to the battery terminal. So if I go across here, you'll see that it's infinite resistance because that contact is open. But if I push down on this, simulating that the coil is energizing and closing the contact, 0.2 ohms, exactly what we want to see. So that contact point is working perfectly fine. On, off. So as long as the resistors on the bottom are doing their job and this coil is okay, then this cutout relay is actually probably going to operate the way it should. So our problem lies right here with these two sets of contact points. We've got to figure out what we can do to make those work. So I just clean these points. Normally I would like to use a point file, but I couldn't find mine, so I ended up using a very fine grit diamond needle file on the rough areas, and then finished it with a little bit of this emery cloth. The emery paper. I could actually see that there was a little raised nub of carbon on the surface of the contact, so that was creating a situation where there was just a little pinpoint area that was making contact. So I had to get that filed out and then dress the surface. So now if I do a resistance check, I think before I had mentioned that these were wired in parallel, but I think because of the resistors in the network, they actually interfere with each other. So to test them, I have to open both of them. So See, if I push both of them open, I get infinite resistance. If I let this one close, I'm now getting about 63 ohms. Previously, I was getting that like 500,000 ohms, so that's a big improvement. Would I like to see it better? Yeah, but I don't want to push those contacts too much. There's only so much meat on them, and they're pretty worn down. And if I open this one and I close this one cleaned up better, obviously, because this one's only measuring 13 ohms. But like I said, I don't want to push this too far, so I'm going to just try it with that. Try it the way it is and see what happens. You know, the other problem is, as I file this contact down, that creates the same effect because it's shortening. The length of that contact that sticks out past this point, that creates the same effect as me adjusting this screw, which I didn't want to get into doing. I did find out a little bit more information online though, and I was able to find out the values of these two resistors, so I can actually test these while I've got the unit out. So I'll do that now. So this long resistor here that's tapped in the middle is actually called a swamping resistor, because this end and this end are directly connected to the base plate of the regulator. They're connected to ground. So in effect, what you really have here is two resistors in parallel with each other going to ground. So if I clip onto my ground connection here and I look at the, I had to clean up an area on here because there's so much oxidation on the metal, but if I get a bare spot of metal, you can see that that's ground, and well, that is ground. It's just, like I said, it's kind of, I think I got a better reading when I clipped on with the alligator clip to this end. There we go. So both ends of that resistor are grounded. So if we take a measurement from the middle to ground, what we're actually looking at right there is we're looking at the resistance of those two resistors in parallel, about 30 ohms. All right, so I actually cleaned that up a little bit better, that connection there. So I'm getting about 20 ohms, and according to what I found for the data for the design data for an RB340, which I don't even know how I stumbled upon this, but it says the swamp resistor measurement is taken on unit between center tag and base. So what I think they mean is, since these two are attached to the base, I think they're calling the center tap the center tag, and on unit means this is in circuit across the other stuff that's going on in here. And that measurement should be apparently 14 to 25 ohms. So I'd say that that swamping resistor is good. This resistor is the contact resistor. There were two different versions of that resistor that were used on these, on this model, probably depending on what type of generator this was hooked up to. Apparently they were identifiable by a color code. The two choices were yellow and red. Well, that looks more red than yellow to me, if you can even get a take a guess on that one. I don't know. That clearly, one end of that resistor is hooked up to here, the armature connection. And so if I go on to the other end of that, get on the field, there we go, it's on the field tab. So that is 11 ohms, and that's actually quite a bit lower than what the design data suggests it should be. Yellow one 37 to 43 ohms, red one 55 to 65 ohms. Interesting. I'd be more concerned if it was higher, because that would indicate that that resistor was open. The fact that it's lower just makes me think again that we're in circuit across something else. I wonder if, yeah, see, if we open if I open the contacts, it pops up to 63. So I think that's actually a 63 ohm resistor. And if that is the red one, then 55 to 65 is what we want to see, so that looks like that's normal. There is a note here. It says that the units controlling 12 volt generators with 4.5 ohm field windings use the yellow resistor for 37 to 43 ohms, and the units controlling 12 volt generators having a 6 ohm field winding uses the red resistor, which is 55 to 65 ohms. I know that's a mouthful, but mainly we just want to make sure these aren't open. All right, I'm going to put it back in the tractor and see what happens. I really can't do any other adjustments because the whole adjustment procedure is pretty elaborate and it requires several pieces of test equipment that I probably could scrounge together from what I have here, but not familiar with these. So I'm just going to hope that cleaning the contacts took care of the issue. Okay, I've got my voltmeter hooked up directly across my battery terminals because that's going to be just as good a place as any to test this, because I've got 12.2 volts on my battery right now, and when I start the engine and the RPMs come up, that voltage should go up to a charging voltage. Of course, the other thing that should happen is when I turn the key on, one of these two lights right here, I forget which one it is, I think it's the left one, is the charge light. That light should go out. Okay, so that's kind of interesting. The voltage isn't going up anywhere near as high as I would expect it to go for the charge. Of course, I'm used to alternators. You know, alternators will kick out around 14.5 volts or so, 14.4, 14 point something anyways. But the voltage is definitely going up. So it could be that the battery is just charged enough that it's just not really drawing current. Drawing enough to cause the regulator to tell that generator to wake up more. So, but the dash light is going out now. As you can see, both of my lights are indicated. One is oil pressure and the other one is the generator light, and once the tractor's started, they'll go out. That's what's normally supposed to happen. Yep, so, well, I thought of something else I can do. After I got the generator working and I was able to fully field it by pulsing 12 volts to the field coil here, and as soon as I did that, the generator woke right up and started making voltage. Well, I noticed that when I was trying to run it with the regulator was not sending any voltage down this wire to the field coil, which is why the generator wasn't working even after I repaired it. So now I can look at what the actual voltage is going to the field coil coming out of the generator as the load changes. So what I'll do is I'll I'll turn the key on, we'll look at what the voltage is, which should be pretty much nothing. And then, oh, so what I was saying was, what I could do is now I can test it. I could see what the regulator sends for field voltage when I start the engine, and then, you know, make sure it's sending field voltage. And then I can put a load on it, which this is a diesel, so the ignition doesn't have an ignition system to draw power. It's just got the gauges and the headlights, but I can turn the headlights on at least and see what happens. So with the key on, we only got 0.17 volts, which is what I would expect. No voltage sent to it yet. All right, well, I'm a little surprised the headlights didn't go a little bit dimmer when I shut the tractor off, but again, maybe my battery's just got plenty of charge in it. That's a huge battery. But I think this is repaired because my lights are going out, so my charging system problem indicator light is going out on the dash when the tractor starts, is what I meant to say. So I think that's going to be it for this repair of the Lucas regulator.